Tutorial 5, Part 3, Strengthening Mechanism. As positive deformations, as I just mentioned, it is governed by the dislocation slip mechanism. And that's how, if we try to hinder such motion, we can decrease the extent of the positive deformation under the same stress. And basically, if we try to decrease such extent, it basically means that the material itself is strengthened and its strength is increased. By increasing the grain density to increase the grain boundary areas, dislocation movement will be hindered by the increased amount of the grain boundaries, and which is we call it grain boundary strengthening. And there is one relationship describes such strengthening. And this term is the material's constant for starting stress for dislocation movement. Ky is a constant. D is the main grain diameter. And basically this one you can consider it as a new strength value or new material constant if there is the increase of the grain numbers. And that means the yield stress is inversely proportional to square roots of the grain size. For smaller grain size, the larger boundary areas. For larger boundary areas, the material is harder and stronger. Work hardening. As I mentioned in the last tutorial, our deformed materials usually have a higher strength. And basically, in actual cases, it is usually co-worked by using the co-worker method. It is because the tangled dislocations will produce new dislocations during positive deformations, which increase the dislocation density. As the dislocation in same phase will generate repulsive force, this will hinder the dislocation motion. And also, larger number of dislocations, it is harder to have dislocation slip. And that is why mathematical expression. The critical result shear stress is equal to the intrinsic strength plus a constant times magnitude of the Berger beta times the shear modulus and times the square root of the dislocation density. And again, you can see that more dislocation density, the strength will increase more. So what is co-work? Basically, it suggests the metals to enough mechanical stress to cause positive deformation. And if you still remember our stress strain curve and elastic recovery, there is actually you can see the relations in the stress strain curve, and actually you can actually see that the yield stress is actually increased, even that you only have the stress strain curve to be observed. And one process to down co-work is rolling. Shrink work hardening. Again, there is some graph from the textbook. Notice the trend for yield strength and ductility. If the yield strength is work hardened to be higher, and that will mean that the ductility will be decreased. If the yield strength is low, that means the materials haven't been cold worked enough, then the ductility will be large enough. As shown here, you can see the corresponding trend for these two graphs. The graph at the left is the yield strength, and the graph at the right is the ductility. Solid solution strengthening. It basically adds some impurities into the materials. When the impurities are added to the host material, based on their size, it will cause different effect on the material. If the size of the impurities is smaller than the host material, it will pose a tensile string around the impurities. If the impurity is larger than the host material, it will pose a compressive string around the impurities, as seen here in these two pictures. This one is the tensile string one, and this one is the compressive string one. Notice the difference in the atom size. And again, this is applied tensile strength or the compressive strength will restrict the dislocation motion, and hence the material itself will be hardened. And metal alloy is a quite straightforward and quite typical example. And again, there is some graph from the textbook. Again, if we add more impurities there, it will have a very similar trend with the string work hardening. Just like if you co-work more, if you add more impurities, the strength will increase more, but the ductility itself will be decreased more. And both youth and tensile strength is increased when we add more and more impurities to have a solid solution strengthening, and while the ductility will be decreased. And again, recalling that ductility is the ease of deformation. Precipitation hardening. Precipitation hardening, H hardening, is a material strengthening technique using material solubility changing mechanism as its working principle. There is some application of this mechanism, such as aluminium, titanium, and steel. The first, the material will be heated to a specific temperature, then it will be quenched immediately. This sudden temperature change will result in a formation of impurities, which is host materials in other phase. Phase will be discussed in tutorial 8, and therefore, these impurities will impede the dislocation slip and strengthen the materials. And impurities of solid solution strengthening is other material, well, those for precipitation hardening is host materials in different phase. That basically means that impurities of the solid solution is added for the other material, but precipitation hardening is basically the same material, but at different part of material, it has different phase. And how can we know that there will be obstruction of the dislocation movement? You can also read from the figure here. Here, the aluminum alloy has a different phase at center, and at the outside here, the aluminum is at a different phase again, and that will produce a tensile or compressive strength, just like the additions of those impurity atoms in the solid solution hardening, and that's basically why this method can also produce materials with higher strength. Temperature effects. When the temperature of a material increases, the kinetic energy of all the atoms will increase, and that means the space between atoms are larger, and that will imply that the dislocation movement will become easier. And that's why the strength at an increased temperature for a material will decrease, and the ductility itself will increase. And here is an example of that picture. Rate effect. Strain rate is the change in strength of a material with respect to time. And there is an example of a high strain rate. If you try to use a hammer to stretch a material, this will apply a large force within a short period of time, which forces the material to deform instantly. Generally, for high strain rate material, it will have a lower ductility but a higher strength. That is because the higher strength rate, there is lower time for dislocation slipping, and the dislocation slip is highly related to ductility. The higher strain rate, the lower ductility. And here is the strain rate effects. For higher strain rate, the yield strength of itself and tensile strength of the material will increase, while the ductility will be decreased.